Most of us grow up with the same picture of the universe. There are stars everywhere, galaxies everywhere, and if you had a powerful enough telescope, you could keep finding more and more things forever. That picture isn't wrong, but it's also heavily influenced by one fact we never think about. We happen to live in a fairly busy part of the universe. The Milky Way has neighbors. The closest large galaxy, Andromeda, is only about 2.5 million light-years away. On human scales, that's an absurd distance, but on cosmic scales, it's nearby enough that astronomers can study it in detail. Because Andromeda is there, and because thousands of other galaxies are visible around us, we've spent the last century building a picture of the universe filled with galaxies. Now imagine changing one thing. Keep the Earth, keep the Sun, keep every human who has ever lived. Move the entire Milky Way to a different address. Put it near the middle of a giant cosmic void, one of the emptiest regions astronomers have ever found. At first, nothing seems different. The night sky still has stars, constellations still exist, the moon still orbits Earth. Then, humanity invents telescopes, and that's where the story changes. When astronomers started mapping the universe in detail, they didn't find galaxies spread evenly in all directions. They found a structure. Galaxies tend to sit in groups. Those groups sit in larger clusters, and those clusters connect through long strands that stretch across space. Between those strands are large gaps where very little is going on. Those gaps are called voids. Most voids are still full of galaxies compared to what empty sounds like in everyday language. Just fewer than you'd expect for that volume of space. But some voids are on a whole nother level. One of the most studied is the Boötes void. It sits in the direction of the constellation Boötes, and it's roughly 330 million light-years across. To put that number into something more grounded, light takes 330 million years to travel from one side to the other. That's longer than the time humans have existed by a huge margin. And inside that volume of space, there are very few galaxies. Not none, but far fewer than a typical region of the universe. If you were to map it out visually, most of what you'd see wouldn't be galaxies at all. It would be distance of space between things that don't really have anything in between them. This is the kind of region our galaxy would be sitting on for this thought experiment. So the question becomes simple. What does everything else look like from inside it? If the Milky Way were placed inside the large void, the first thing that would change isn't anything on Earth. It's what happens when humanity starts looking outward. Right now, even small telescopes can pick up other galaxies. They look like faint smudges at first, then clearer shapes once instruments improve. Over time, that gave astronomers a second layer of the universe to study, beyond the Milky Way. That second layer is what made modern cosmology possible. It gave us other galaxies to compare with our own. It gave us a sense of scale. It showed us that the Milky Way is just one system among many. Inside a large void, that early progress would look different. The nearest large galaxies outside your local area could be so far away that early telescopes wouldn't detect them at all. Not because they aren't there, but because the distance is doing most of the work. For a long time, astronomy would stay locked inside the Milky Way. Star clusters, nebulae, the structure of our own galaxy. That would be the entire observable universe for generations. And without clear evidence of other galaxies nearby, one of the biggest ideas in science would take much longer to arrive. The idea that the Milky Way is not the whole system. If you only had one galaxy to study, a lot of modern astronomy becomes harder to build. Right now we understand galaxies by comparing them. Spiral galaxies next to elliptical ones, small galaxies next to large ones, quiet galaxies next to ones actively forming stars. Those comparisons are what led us to build classification systems and understand how galaxies change over time. Without nearby galaxies, that whole framework disappears. You would still see stars forming and dying. You would still map dust clouds, star clusters, and the structure of the Milky Way in detail. In some ways, your knowledge of your own galaxy would go deeper than ours today. But it would also be limited to a single case. Even basic questions start to shift. You wouldn't know if the Milky Way is the typical or unusual. You wouldn't know if its size is normal. You wouldn't know if its structure is common or rare. Everything would feel like local behavior instead of part of a larger pattern. And when distant galaxies eventually became visible, they would arrive as a surprise rather than something expected. A few faint objects in the sky, far beyond anything mapped before. Not part of a known structure, just isolated points of light at extreme distances. That moment would reshape everything, because it would be the first time you realize the universe is bigger than the system you live in. At some point, technology improves enough that those faint smudges in the sky start to resolve into something clear, individual galaxies. Not part of the Milky Way, not star clusters, entire systems of stars, held together by gravity, far beyond anything in our local region. The first reaction wouldn't be excitement about a new category of object, it would be distance, because even the closest of these galaxies would be extremely far away compared to everything previously mapped. The sky would stop being something that feels contained inside the Milky Way and start becoming layered. Local stars in one layer, dust clouds in another, and then, far beyond, everything else. From inside a void, that separation becomes even sharper. There wouldn't be a gradual transition from Milky Way objects to external galaxies. It would be a jump. One moment everything is inside your galaxies, the next moment everything is far outside it. And once those galaxies are mapped, a new realization becomes unavoidable. They are not scattered randomly close to you. They belong to structures that stretch far beyond what your local region contains. Large-scale patterns of matter that were invisible before this point. The universe doesn't just contain galaxies, it contains regions where galaxies are concentrated, and regions where they are almost all absent. And the Milky Way, in this version of reality, sits deep inside one of those empty regions. Once those distant galaxies are finally detected, the first thing that changes isn't just what we see, it's how far away everything turns out to be. Inside a region like a cosmic void, the nearest large galaxies outside the Milky Way wouldn't be nearby targets like Andromeda or the Triangulum galaxy. They would sit far beyond what early observations are used to dealing with. Distances that normally feel manageable in astronomy would stretch into something harder to compare with anything in the local universe. At that point, mapping the sky stops being a matter of identifying nearby objects and starts becoming a problem of range. Where does one structure end and another begin when everything is separated by hundreds of millions of light years? This is where the idea of the cosmic web becomes important again. Galaxies aren't just scattered randomly through space, they follow long filaments shaped by gravity. Between those filaments are regions with far fewer galaxies. So what you're seeing isn't just faraway galaxies, you're seeing the edges of structure itself. From inside a void, those structures would appear thin and distant, isolated points that only begin to make sense when you realize they are part of something much larger, and that leads to a simple but uncomfortable realization. Your galaxy isn't just far away from others, it's sitting in a region where there are very few others to begin with. Before large-scale astronomy, the universe would look very different from what we know today. You would still have stars, nebulae, and everything inside the Milky Way. That part of astronomy develops the same way it did for us. But beyond that, there would be very little evidence that anything else exists. Even after the first faint galaxies are detected, they would appear so distant and so sparse that they wouldn't immediately form a clear pattern, just a handful of objects scattered across deep space. Without a dense cosmic neighborhood, it becomes harder to build the idea that galaxies are common. It also changes how you interpret what you see. In our actual universe, the Milky Way sits in a region where other galaxies are relatively close, which makes it easier to recognize patterns like clusters and filaments. In a void, that context is missing, so the early model of the universe would likely stay small for longer, centered on what can be observed directly rather than what can be inferred from surrounding structure. This doesn't stop progress, but it slows the step where astronomy shifts from studying the galaxy to studying the universe. And that delay matters, because a lot of modern cosmology depends on having multiple reference points. Redshift, galaxy motion, large-scale expansion. All of it becomes clearer when you can compare many systems across different distances. Without that, the universe still exists in the data. It just takes longer for anyone to see it clearly. At some point, technology improves enough that distant galaxies are no longer just faint smudges. They start to show structure, shapes, rotation, light that can be broken into spectra and measured. That's when redshift becomes important. Astronomers notice that the light from distant galaxies is stretched. The farther away a galaxy is, the more its light shifts towards the red end of the spectrum. From there, a pattern emerges. Galaxies aren't just sitting still, they're moving away from us, and the farther they are, the faster they seem to recede. This is one of the key observations that leads to the idea of an expanding universe. Inside a void, this discovery would still happen. The physics doesn't depend on location, light still behaves the same way. Spectra still shift the same way. But the road to that conclusion would look different. Fewer nearby galaxies means fewer early comparisons, fewer reference points for distance, fewer stepping stones for we see a few strange objects to this is the universe-wide pattern. So the idea of expansion would likely arrive later in history, after enough distant systems were finally mapped with enough accuracy to show the trend clearly. And once it does arrive, it brings a shift in perspective. The universe isn't static, it's changing on scales far beyond anything visible in a single galaxy. At that point, the question stops being about what exists nearby. It becomes about the overall structure of everything that exists. Once enough galaxies are mapped, a pattern becomes hard to miss. Galaxies aren't evenly spread out through space, they collect into clusters. Those clusters connect into long filaments. Between those filaments are large gaps where very little is found. This structure stretches across the observable universe. From this point of view, the Bode's void and other regions like it aren't unusual accidents. They're part of the same pattern that shapes everything on the largest scales. Matter in the universe has been slowly pulled together by gravity for billions of years. Dense regions became denser, empty regions became emptier. What remains is a kind of network, a cosmic structure defined as much by what isn't there as what is. If the Milky Way had formed inside one of the emptier regions, that structure would still exist. It would just take longer to see it clearly. The universe wouldn't look different in reality, only in how quickly its shape becomes obvious. And that leads into the final idea this whole thought experiment has been building toward. The universe has the same structure everywhere. Gravity works the same way, light travels the same way, galaxies form and evolve under the same rules. But understanding that structure depends on where you begin. We live in a part of the universe where nearby galaxies are visible and accessible to observation. That made it possible to build a picture of something much larger than our own galaxy. From another location, especially inside a large cosmic void, that path wouldn't look as direct. The same universe would still be there, the same galaxies, the same expansion, the same large-scale structure. What changes is how long it takes to reach those conclusions, and what the sky looks like when you're trying to figure it out. So when we look at the night sky and see galaxies scattered across space, it's easy to assume that this is what the universe naturally looks like from anywhere. But that view depends on where we are. Somewhere else in the universe, the same questions might take longer to answer, or start from a completely different set of assumptions. And if we had formed there instead, our understanding of everything we see today might have taken a very different path to get here. The universe stays the same. Our starting point doesn't. Thanks for watching, and I'll see you in the next one.